okay, integration. So a bit more complicated and involving trigonometry. So obviously you have your wheel that you can use to help remind yourself about differentiating and integrating. Remember, integration is your anti-clockwise option. So using this, if you don't have any kind of complicated integrals, you know the integral of cos is sine. So your integral of cos 3x is going to be a third sine 3x. You know your integral of sine is minus cos. So obviously you would divide by the derivative of your x. So you would divide by a half. And it's just if you had a bit of a multiple there. So I've put another simple integral using trig. Right. So you are going to have to be expected to use trig identities to perform certain integrals. So it used to be very much in the old A level that the biggies were integrating of sine x squared and cos x squared. Now you can't use reverse chain rule on these, because if you thought about how they were written, sine x in brackets all squared, the function inside the bracket is not linear. Sine x is not linear and cos x is not linear, so they've got to be rewritten using identities, and the big identity that you use are the cos 2a identities. So they're the two that you need to be really confident with. So if I want to do straightforward integration of sine x all squared, then you would rewrite using your cos 2x identity. So you would rewrite that, and then you would be able to integrate that function in straightforward fashion. And again, I've got one without limits, so you'd have to remember your plus c. You then, if you had something, a multiple of your angle, so here we've got the integral of 3 cos 4x all squared, and then you would rewrite that using your cos 2a. I like using the 2a so that I can replace my angle more easily, and now I'm substituting. I know that 2 cos squared a is cos 2a plus 1, so 3 cos squared a is 3 over 2 of that angle of cos 2a plus 1. And I'm now going to replace my a with 4x. So the cos of 4x all squared times 3 is 3 over 2 times the cos of ax plus 1. So you've been able to rewrite that, and now you can integrate it. So rewriting your integral, you can then integrate your function and then multiply all by 3 over 2. Tan x all squared, so that's not one that you can integrate, but you can rewrite it using your identity. And sec squared x is one that you can integrate. You know that the derivative of tan x is sec squared x, and you can, so therefore you can rewrite your integral and then integrate sec x all squared minus 1. That's going to give you tan x minus x, and I've put my plus c there. So that's using identities. Right, substitution. Now, in the past, you would have been told what substitution to make, and you still might be, but you might not. That's the new thing on the new A level. So here's one where I've been told what substitution to make, and it's substitution with limits. So I've been told that I'm going to make the substitution u is 2x plus 1. So the first thing I'm going to do is replace my x limits for u limits. So I've done that, made that very clear. That's going to get me marks. I then find du dx, and then I'm going to rewrite that. And I can't decide until I've really looked at the question which is going to be most useful to me. So I'm going to play it by ear. I've rewritten them both. I know that 2x is u minus 1, so 4x is going to be 2 times that. Now, I multiplied them both by 2, but I may have to take out a factor, and when I substitute that back into my integral, I've spotted that I probably would have been better off leaving it as 2 bracket u minus 1 instead of writing it as 2u minus 2, but absolutely fine. I just rewrite it, and then I've ended up with a much more straightforward integral. Now, I then substitute my limits in, and I've ended up with that exact answer. You may not be told what substitution to make. That's much harder, and that's new to the A level. And here I've got one without limits. So we tend to use our inner function for our substitution, and our inner function would very definitely be the 5x minus 6. That's what's making this such a hard integral. So I'm going to let u equal 5x minus 6. So I find du dx, and then I rewrite. And again, I'm not really sure how I want to write this. So I'm going to just sort of play it by ear and see how it pans out. Now I know that 5x is u plus 6, so x is going to be a fifth of u plus 6, which I've written like that. X plus 1 will add 1 to both sides, so I've managed to rewrite it like that. So my integral, making my substitutions and replacing my dx with a fifth du, is going to look like this. I multiply all my terms by a fifth, so I've ended up, and obviously using the laws of indices, that's what I've ended up with to integrate. I've taken out a factor of 1 over 25, leaving me with that integral, and now I'm going to integrate it, just raising the power by 1, dividing by the new power. So I think that's what we end up with. Raising the power by 1, dividing by the new power, substitute back in, and it's quite ugly, and then multiply everything by 1 over 25. So you end up with quite an ugly answer. There have been a few really difficult ones using trig substitution, so you might be told what trig substitution to make, but you might not. So here's one with limits, and you are going to spot that it's written in the form where it looks a bit like 1 minus sine squared or 1 minus cos squared. So making the substitution, and they may well have told you to make the substitution, which would be good. I'm using the substitution x equals 3 sine theta. So dx d theta is 3 cos theta. So I've rewritten that to make dx a subject. I'm changing my limits. So when x is 3, sine theta will be 1, in which case theta is pi over 2. When x is 0, theta is 0. So you replace your values in your integral with your theta values, and it's going to look like that. Now, this is why this substitution was made. So you know, taking out a factor of 9, it's going to leave you with 9 bracket 1 minus sine squared theta. Using your laws of surd, you can split that up as a product, and that's going to give you 3 cos theta. You then substitute that back in, and that's what your integral becomes. I've taken a factor of 9 out, and now you are just integrating cos squared theta. And obviously we integrated that a moment ago by rewriting it using double angles, so I'm not going to go over that again. And that's me integrating it and substituting my limits in. However, you might have been asked to do that without limits. That's much, much harder because you're going to have to substitute back in for x at the end. You make the same substitution, you integrate it in exactly the same way. So I've used exactly the same method and got to there. Now, unfortunately, I don't have theta values to put in. I need to substitute back in for x. Now, that's much harder. You know that sine 2 theta is 2 sine theta cos theta. So you go to your substitution. You know that sine theta will be x over 3. You then use your identity, cos squared plus sine squared is 1, and you rewrite it to make cos theta the subject. So you know that if sine theta is x over 3, then sine squared theta will be x squared over 3 squared, x squared over 9. So you're able to rewrite cos theta like that. So when you go back to your sine 2 theta, it's going to be 2 times sine theta times cos theta. Substituting that back into your integral, you're going to get an ugly thing that looks like that. You know that theta is going to be the inverse sine of x over 3. Now, neatening up that square root, this is in case they've asked you to get an answer that looks like something else. I've put that over a common denominator, then square rooted it, so I've just neatened it up a little bit, substituted it back in. I would say that that's going to be your neatest version of your answer. Parametric integration, okay? So parametric integration, you're simply going to have something that looks, if you have the integral of y with respect to x, that needs to be written as the integral of y, and it's times dx dt, and that's integrated with respect to t. So here's one where you have to find your limits. You've been given x and y parametrically, x equals 4t and y equals sec t all squared minus 2. Now, I don't know what the limits are on that x-axis, and I'm going to need them in terms of t. I do know it's when y equals 0, so I'll let y equal 0. I'm going to solve that, so that was going to make sec t all squared equal 2. And sec's 1 over cos, so I take the reciprocal of both sides. I'm going to have cos t all squared is a half, so cos t is plus or minus the square root of a half. So that's going to be plus or minus square root of root 2 over 2. I know that t will be pi over 4 and minus pi over 4. So they're my limits. So I put those in, I replace, I've got y, my integral of y, I've got dx dt, and that's all going to be integrated with respect to t. I know the integral of sec squared is tan, so I end up with 4 bracket tan t minus 2t, and I substitute my limits in. So substituting in my limits, I've ended up with 4 bracket 2 minus pi, close bracket, or 8 minus 4 pi.